Good evening, everyone. My name is Hiba Idris, and I'm here presenting with my group members, Mubarak, Mabur, and Yusuf. Together, we'll be talking about the Java Virtual Machine, also known as the JVM. For my part of the presentation, I'll be focusing on three main things: a short history of Java, the structure of the Java class, and how bytecode works inside the JVM. This topic is really interesting because it explains one of the biggest reasons Java has stayed powerful and relevant for so long. It can run the same program on any device or computer without changing the code. Java was created in the early 1990s at a company called Sun Microsystems. A team of engineers led by James Gosling started a project called the Green Project between 1991 and 1995. Their goal was to create a new kind of programming language, one that was simple, secure, and could run on any device. No matter what kind of computer or operating system you had. At first, the language was called Oak, named after an oak tree outside of Gasoling's office. But later, they changed the name to Java, inspired by coffee beans. The name Java was meant to represent energy, simplicity, and creativity, things they wanted their language to reflect. Unlike older languages such as C or C++, Java didn't need to be rewritten for every system. You can write the program once and it could run anywhere because of the JVM. Thus, where the famous slogan comes from: write once and run anywhere. This idea was revolutionary and became the reason Java is still so popular and important today. Java's official launch. Java officially launched in 1995, and it couldn't have come at a better time. The internet was just starting to explode in popularity. One of Java's biggest features was the Java applet, a small program that could run right inside a web browser. Back then, websites were mostly just text and images, but Java applets made it possible to add animations, mini games, and interactive tools directly to web pages. Java also introduced automatic memory management handled by something called the garbage collector. This meant programmers no longer had to worry about freeing up memory themselves. The program handled it automatically. This made programs safer and less likely to crash. Another major thing was Java's security. It ran programs inside a sandbox, which is a protected environment that stopped harmful code from damaging your computer. Even though applets aren't used anymore today, they played a huge role in helping Java grow and shape the way modern programming works. As the years went by, Java continued to improve. In 2006, Sun Microsystems made a big decision. They made Java open source, which meant anyone could look at the code, use it for free, and even help improve it. This opened Java to a global community of developers. Then in 2010, the company Oracle bought Sun Microsystems and took over Java's development. Since then, Oracle has continued to release new versions of Java regularly, adding new features, improving performance, and making it more secure. Today, Java is literally everywhere. It powers Android apps, banking systems, and cloud service, scientific tools, and big data platforms. It's also one of the first languages students learn in college because it's great for teaching object-oriented programming, the foundation of many modern languages. Even after almost 30 years, Java remains one of the top programming languages in the world, and thus mostly because of the JVM. How Java works internally. So now, let's look at how Java actually works behind the scenes. When you write a Java program like Hello World, that's called your source code, basically the text you write. The Java compiler called Javac takes the source code and turns it into something called bytecode, which is stored in a .class file. So this bytecode isn't tied to any one computer, it's a universal language that any JVM can understand. When you run your program, the JVM reads this bytecode and executes it. Sometimes it reads it line by line, and other times it uses something called a just-in-time compiler to turn it into native machine code for faster performance. This process is what makes Java platform independent. You can run the same program on Windows, Mac, Linux, or even your phone. It'll work the same way everywhere. The JVM is made up of several main parts that all work together. The first thing is a class loader subsystems. This part loads .class file into memory. When the program starts, it makes sure each class is only loaded once. Second, runtime data areas. This is the memory section inside the JVM. It has several parts: the method area, which stores class level data, the heap, which stores all the objects created while the program is running, and the stack, which keeps track of method calls and local variables. The third is execution engine. This is basically the brain of the JVM. It includes the interpreter, which runs the bytecode line by line, and the just-in-time compiler, which makes program run faster by turning commonly used code into native instructions. And then fourth is the Java native interface. This allows Java to work with other programming languages like C or C++ when needed for performance or hardware level access. If you look at this diagram, you'll see how everything connects. The class loader brings the compile.class files into memory. The runtime data areas store information and data while the program is running. The execution engine actually runs the bytecode and handles performance. The Java native interface allows Java to communicate with code written in other languages. This design is what gives Java one of its big strengths, which is consistency. No matter where you run your program on Windows, Mac, or Linux, the JVM makes sure it behaves exactly the same way. It's like basically having a translator who understands every computer's language. So every time you compile a Java program, the compiler creates a .class file. This file is binary file that contains all the bytecode, the instructions for the JVM. The .class file follows strict rules defined by the JVM. It starts with a magic number written as this this number, which tells the JVM that this is a valid Java file. Next, it includes version information, which tells what version of Java was used to compile it, like Java 8 or Java 17. After that, there's the constant pool, which stores things like strings, method names, and class reference. Then there are access flags, class information, and finally fields, methods, and attributes. All of these sections together help the JVM understand how to run the program correctly. The first thing inside every class file is the magic number. This acts like a signature that says, yes, this is a real file, Java file. If the JVM doesn't see this number, it won't even try to run the file. This helps prevent corrupted or harmful code from running. After the magic number comes the version information. This tells the JVM which Java version was used to compile the file. For example, version 52 means the file was compiled using Java 8, and version 61 means Java 17. This helps the JVM make sure everything is compatible before it runs the program. The constant pool is one of the most important parts of the class file. Think of it like a big reference table where all the important constants in the program are stored, like text strings, numbers, methods, names, and class files. Instead of writing the same name or value many times in the file, Java stores it once in the constant pool and just points to it whenever needed. For example, if your system calls system.out.println several times, it's stored only once in the constant pool. This design makes Java programs smaller, faster, and more efficient. It helps the JVM find things more quickly than the program when the program runs. After the constant pool, we get to the fields, methods, and attributes sections. Fields are the variables that belong to the class. Methods are the actions or functions that the class can perform. Each method contains the actual bytecode that tells the JVM what to do. Attributes store extra details like line numbers used for debugging and method information such as size or code length. Together, these sections give the JVM all the details it needs to understand and run the program correctly. Let's look at a simple example, bytecode example. If you write this in Java, this code, each line is an instruction for the JVM. Get static gets the output stream, and IDC loads the string LDC loads the string hello world. Invoke virtual calls the println method and return ends the method. So no matter where you run this on Windows, Mac, or Linux, this bytecode stays exactly the same. The JVM handles the translation into the machine's native language. So why bytecode matters? Bytecode is the key to what makes Java so powerful. Because the JVM runs any bytecode, it goes through a bytecode verifier. This verifier checks to make sure the code is safe, that it's not trying to access memory it shouldn't, or doing anything dangerous. After that, the just-in-time compiler starts optimizing the code while the program runs. Um, it learns it learns which parts of the program are used the most and turns them into native machine code for even faster performance. That means the longer your program runs, the more efficient it becomes. So bytecode doesn't just make Java portable, it also makes it secure, reliable, and fast. So Java was designed to be portable, secure, and efficient, and the JVM is the technology that makes all of that possible. It allows Java program to run anywhere in the world on any operating system without needing to change the code. We looked at how Java started and evolved, how the JVM loads and runs class files, and how bytecode connects what humans write to what computers actually understand. Even after almost 30 years, Java is still one of the most used and respected programming language, and it's all because of the JVM.
Hello guys, my name is Mubarak Idris and I'll be discussing I'm a part of group 5 and our topic is Java Virtual Machine. The two topics on Java Virtual Machine that I will be discussing are Java memory management and Java implementations such as platforms and vendors. Java memory management in the JVM. The Java Virtual Machine automatically manages memory. This means that programmers don't have to manually allocate or free memory, unlike in C or C++. The JVM divides memory into several runtime areas like the heap, stack, and method area, which helps organize data efficiently. This automation reduces the risks of crashes or memory leaks and allows Java programs to run the same way on any operating system. JVM runtime data areas. The JVM organizes memory into five key regions called the runtime data areas. The method area, um, the method area holds information about classes that are loaded by the JVM, things like class names, method code, and static variables that belong to the class. The heap is where all Java objects and arrays live. It's shared across threads and automatically managed by the garbage collector. Each thread also has its own Java stack, which keeps track of method calls and local variables. Every method call creates what's called a stack frame that stores that method's data. The program counter register or PC register keeps track of the next instruction to execute for each thread. Lastly, the native method stack supports native code written in other languages like C or C++, which Java sometimes relies on. All of these areas together form the foundation of how the JVM stores and manages data while a program runs. The Java heap and generational memory. The heap is the largest part of the JVM memory, and it's where all objects and arrays created during program execution are stored. To make garbage collection faster and more efficient, the heap is divided into different sections known as generations. A young generation is where new objects are first created. Most of these objects don't last very long. They're quickly discarded, so the garbage collector can clean the space frequently. Objects that survive several garbage collection cycles are moved to the old generation or tenured space. These are typically long-lived objects that remain in use for a while. Modern JVMs also include metaspace, which stores metadata about classes such as method names and structure instead of using the older PermGen area. This generational setup helps balance memory performance. The JVM can quickly reclaim short-lived objects while minimizing pauses for older, stable ones. Garbage collection and memory tuning. The garbage collector or GC is one of the JVM's most powerful features. Its job is to automatically free up memory by removing objects that are no longer reachable in the program. Early garbage collectors used the mark and sweep algorithm, which scans memory, marks active objects, and deletes everything unmarked. Another method is the copying collector, which moves live objects to a new space and then clears the old one. This reduces fragmentations. Today's JVMs use generational garbage collection, which treats young and old objects differently to make cleanup faster. Modern collectors like G1, GC, ZGC, and Shenandoah are optimized for multi-core processors and large heaps. They aim to minimize stop-the-world pauses so applications keep running smoothly. Developers can also tune the GC using command line options, such as dash XMS, which sets the starting heap size, and dash XMX sets the maximum heap size, and dash XS XX plus and plus use G1 GC chooses the G1 collector. Tools such as JCouncil, Visual VM, and JStat allow monitoring of garbage collection performance in real time. Altogether, garbage collection and tuning options make memory management both automatic and flexible for different system needs. Why memory management matters. Memory management might sound technical, but it's one of the main reasons Java is reliable. Automatic garbage collection and organized memory areas prevent memory leaks and reduce the chance of programs crashing. By handling allocation and cleanup automatically, the JVM lets the developers focus on writing code instead of worrying about freeing memory like in C or C++. This design also improves performance because the JVM can optimize how memory is reused while keeping programs stable. Finally, memory management is a big part of what makes Java portable. A Java program can run on any operating system without changing the code, and the JVM takes care of all the low-level memory work behind the scenes. So overall, memory management keeps Java efficient, safe, and consistent wherever it runs. JVM implementations and the Java specification. The Java virtual machine isn't just one single program, it's a specification, which means it's a detailed set of rules describing how the JVM should behave. Different companies and organizations can build their own versions of the JVM as long as they follow this official spec. That's why you'll hear about JVMs from Oracle, Eclipse, or Amazon. They all run on Java bytecode the same way, but each might optimize performance or memory differently. For example, one version might start faster while another might use less memory or work better for servers. This idea, one specification, many implementations, is what lets Java programs run on any platform that has a compatible JVM, which is the core of Java's write once, run anywhere philosophy. There are several well-known JVM implementations that all follow the same Java specification but serve different goals. The most common one is Hotspot, which comes with the official JDK and OpenJDK. It's optimized for overall performance and is basically the default JVM that most people use. Eclipse OpenJ9, originally developed by IBM, focuses on being lightweight. It starts up faster and uses less memory, which is helpful for cloud or container environments. GraalVM or Oracle Labs is one of the newer JVMs. It's designed for high performance and can even run on other languages like Python, JavaScript, and Ruby on the same runtime. Um, it also supports ahead of time or AOT compilation for faster startup. Azul, Zulu, and Azul Prime are commercial versions made by Azul Systems. They're tuned for industries that need super low latency responses like trading systems. And finally, Amazon Corretto is AWS's free build of OpenJDK, which guarantees long-term support and stability for cloud-based Java applications. So while all of these JVMs run the same bytecode, each is optimized for different needs from general use to enterprise level performance. Platforms and performance differences. Java virtual machines are used on all kinds of from personal computers to huge servers, cloud systems, and even mobile devices. The Hotspot JVM is a standard for most desktops and servers. It offers strong performance and stability, which is why it's still a default choice in most environments. OpenJ9 is great for modern cloud computing. It uses less memory and starts up faster, which is perfect when you're running many small instances or containers. Graal VM is built for high performance and flexibility. It can run multiple languages, not just Java, and uses just in-time compiler that makes long-running programs extremely fast. Even Android ART is inspired by the JVM. It compiles apps ahead of time into native code instead of interpreting bytecode, which helps Android apps start quickly and run smoothly. So overall, each JVM platform focuses on different balances, startup time, memory use, or peak performance, depending on where it's deployed. To sum everything up, all the JVMs follow the same core design, but each one adds its own strengths. Some are built for speed, others for low memory use, or for running in the cloud. But no matter who makes it, every JVM runs Java bytecode the same way. Combined with Java's automatic memory management, this gives us reliability, safety, and portability. The reason Java can run on almost any system. So when we say write once, run anywhere, it's really the JVM that makes that promise possible. These are the main sources I use for my section. The Oracle Java Virtual Machine specification explains how a JVM is structured, things like the method area, heap, and stack, which I used when talking about memory management. The Eclipse OpenJ9 and Graal VM documentation helped me compare different JVM implementations and how each one handles performance. Azul Systems Platform Prime overview showed how some companies design commercial JVMs for really fast or low latency systems like in finance or cloud computing. And the Amazon Corretto docs were useful for understanding how Java runs in cloud environments using AWS's OpenJDK build. So overall, these are all official sources from the main JVM vendors, and they helped me make sure everything I presented was accurate and up to date. And that's all I have for today.
Hello, my name is Yusuf Abdul Qadir, and in my section, I will be doing Android implementation, just-in-time compiler slash execution. So, why? So, Android doesn't use the regular Java virtual machine because the regular Java virtual machine isn't really optimal for Android devices. For they made a Android made its own version called Android Runtime, and because regular Java Virtual Machine was made for devices with more RAM, more CPU power, and more battery constraints. So they made a more efficient version that takes up less power and fewer battery constraints, and so it can be more efficient for mobile devices, because standard Java virtual machine is made for desktops and like server systems, so it wouldn't have been optimal for mobile devices. And it comes from Android Runtime, evolves from Dalvik virtual machine, which was created before it. These are three different types of virtual machine: the regular one, the Dalvik virtual machine, and Android Runtime. So the virtual machine, the Java virtual machine, is made for desktops and server systems, while the Dalvik virtual machine runs for Androids versions 4.4 and earlier, while the Android Runtime is still used on regular systems today. And the Java virtual machine uses a stack-based system, which is a system that executes instructions and operands at the top of the stack, while Dalvik's virtual machine uses register-based architecture, which requires a mixture of both, where it needs one operand and in the register and one in the memory. And the same thing for Android runtime. And Java's virtual machine is not optimized for battery because it's meant for higher end stuff, while Dalvic's virtual machine, it was optimized for the time when and the AU was ran on the Android, and the regular Android runtime is more optimized for its battery. And then for Java's virtual machine it runs normal applications speeds while downloading. And then Dalvik is optimized for Android, so it's gonna do faster than if it was on the Java virtual machine. And the fastest is the Android runtime because it's the more modern. And Java as a virtual machine is not optimized for mobile devices, while Android runtime is optimized, and Dalvic's virtual machine is from the past. How Android runtime improves performance compared to Dalvic's virtual machine. It uses something called ahead of time, which processes the machine level instruction before the application runs, which helps it startup times improve by compiling the code, pre-compiling the code, which reduces runtime performance. It improves garbage collection by optimizing the collection, and improves the memory management and making apps more efficient to be run. Is more efficient memory because its memory consumption is reduced by optimizing the execution process and reusing the compiling code across the different apps. The process of just-in-time compilation, it gets the source code, it runs it through the compiler because it needs the bytecode to run it in the just-in-time compiler. So then it runs the application, and then it identifies hot codes that are common, and then it turns them hot codes into machine code, which it will execute its normal native code. What can just-in-time compiler do? It compiles the code during the runtime, which it can edit and change stuff, and then it compiles the bytecode into its native language while it's running, and supports dynamic behaviors and becomes adaptive. So if it needs to change something while it's running, it can do that. The difference between ahead of time versus just in time is that the pros are like in ahead of time, its startup performance is faster because it's already done the code, and it has better security because it dead the code while it's not be able to be manipulated while running it, and then it reduces the non-used codes, which happens. But the cons is it takes up a lot of build-up time, which is increased a lot in the build. It has limited flexibility because it's doing all the code before it runs, but in just in time, it's more flexible because it's doing the code while it's running, and it can be fixed and changed, and then it reduces build up time because of that, and it has adaptive coding, which the coding, so its development speed is quicker and it can be changed. But the cons are it has longer startups and slower executions because it's doing two things at once. Example of JIT just in time is Google V8 has 3 steps in the just in time application process. So in its 3 steps, it has the parsing and compilation, which is the first step it has to do to get the JavaScript code and translate it into a immediate represent. And in the machine code, intermediate representation is in the compiler into a machine code, and it's known as optimization code. And in this unoptimization code, it runs faster than the interpreted code, but not fully optimized. And in function optimization is the second step which it does, and in the second step, a compiler uses a technique called incline catching, which is a type of catch that of an object passes through a function to be used in a. The more a function is called, the more optimized it becomes. And then its last step is code generation, which allows the machine code to be optimized in techniques, and it's called, it has names like hidden classes and incline catching. Hidden classes also allows the allocate memory to become more efficient and reduces its garbage collection, which is the purpose of catching and optimizing and looking for objects, and to reduce times and property accesses. So just in time has some security features because it is running code and updating code at the same time, so it needs some features to help give it protection. So one thing is that it gives limited access for a specific time period, and this reduces surface level attacks, so they can't just put malicious code right into it while it's operating the code. It uses something called a granular control, which allows it to have permission for each user, and it has really tight management over who gets access of it. And it also has it uses something called automatic workflows, which is a really important role in just in time for it to be safe, and it revolves around revoking access without manually intervention. And these automatic systems enhances its efficiency and its reliability by making rules and conditions for it to reduces human error and make it more safe. So, in summary, Android uses runtimes instead of Java virtual machine because of its efficiency and how it needs to be more optimized for a smaller device with less RAM, less CPU power, and of Android runtime evolving from Dalvik virtual machine because of how outdated that system and how this new system is more efficient for Android devices, and how just in time is used and how it's processed through its compilation process, and how just in time is used into Google's V8 system, how just in time can be safe, and because it's doing code times process because it's very vulnerable to malicious code. And this is my reference.
All right. What is just in time? Just in time is a part of the Java virtual machine that takes Java bytecode and compiles the more frequently used parts of the program into native machine code while the program is running. So it's built into the Java virtual machine, and when we run a Java program, it doesn't immediately become native machine code. Like C or C++ does. Instead, Java first uses or compiles the program into something called a bytecode, which the JVM reads. And the goal is to improve the performance of Java applications by reducing the overhead of interpreting bytecode instruction by instruction. It optimizes hot methods based on real runtime behavior. And this is what allows it to approach the performance of languages like C and C++. So when we write Java code, we first compile it using the Java compiler. This turns the source code into bytecode and stores it into a .class file. The Java virtual machine loads the bytecode into memory when the program starts. As the program runs, the JVM profiles the code and identifies methods and loops that run frequently, so hotspots. The JIT compiler then compiles these hotspots from the bytecode into native machine code for the CPU. The native code is cached and reused, so future executions run much faster than the interpretation by itself. And that's what makes it faster than just pure interpretation. When the Java program is written, it's first compiled by the Java compiler from human readable source code into bytecode, and the bytecode is stored into a .class file. Bytecode is it's a platform independent intermediate instruction set that is understood by the JVM. It's not tied to any specific operating system or CPU, which is what allows Java programs to be write once, run anywhere. And as the program is running, JVM loads the bytecode into memory. The JIT compiler analyzes the running program and looks for hot methods and loops that are executed many times. Once identified, the JIT compiler translates these hot sections of bytecode into native machine code. After this compilation, the JVM can execute the native machine code directly. which is much faster than interpreting bytecode instruction by instruction. All right. So without JIT, Java uses only the interpreter inside the JVM. The Java source code is compiled into the bytecode, and then the JVM reads and interprets each bytecode instruction one by one. This adds overhead because the JVM must repeatedly decode and execute each instruction, and there's no native machine code that is generated, so the program does not get faster over time. And this interpreter only path is significantly slower than running native machine code, such as C or C++. And so this model just basically goes from source code to compiler to bytecode, which takes a lot longer than using JIT. So here's just a simple Java program that prints hello to the screen. And whenever we compile this program, the Java compiler creates a class file that contains the bytecode, and this bytecode is what the JVM actually reads and executes. And so this is what the bytecode would pretty much look like from the program before. So in the instruction or the constructor section, a load _0 loads the this reference. Invoke special calls the parent class constructor, which is object. And then return ends the constructor. And then for the main method, get static loads the system.out, which allows us to print to the console. LDC loads the string hello with the exclamation. Invoke virtual calls the print line method on system.out, and then return finishes the main method. And then the numbers on the left side are the bytecode instruction offsets, and these represent the byte positions where each instruction begins in memory inside the method. C++ performance. So C++ works differently. C++ code is compiled directly into native machine code that the CPU can execute almost immediately. There is no virtual machine and no bytecode, and that's what gives C++ very fast startup times and consistently high performance. And then the operating system and CPU execute immediately. And C++ is often the fastest language for computational tasks, operating systems, real-time systems, and anything that requires low-level control. Java bytecode on its own is slower because it must be interpreted instruction by instruction. This creates overhead that C++ does not have. But with JIT enabled, Java becomes much faster. The JVM profiles the running program, finds frequently executed code or hot codes, and compiles them into the native machine code. And the JVM also caches this compiled code, so future executions run extremely fast. And so that's why long-running Java programs like servers or applications can approach or even match C++ performance in many cases. So here's kind of just a comparison of this comparison summary of Java and C++. C and C++ are usually faster because they compile directly into native machine code and run without a virtual machine. Java compiles to platform-independent bytecode, which is slower when interpreted. However, with the JIT compiler, the JVM can translate frequently executed bytecode into the native machine code at runtime and allows Java to approach the performance of C and C++ in long-running applications. And so the big difference is C++ is fast and immediately because it's natively compiled, and Java gets faster over time because the JIT optimizes it during runtime. And this diagram compares Java and C running the same scientific benchmarks. C compiles directly to native machine code and is usually faster, and achieves performance close, or Java with JIT performs close to C in many different workloads. This demonstrates that while interpreted Java bytecode is slower, JIT optimized Java can approach native C++ performance in long running computational heavy uh, applications. So this is just basically a summary of the topics that I talked about. So Java compiles source code into platform independent bytecode, not machine code, when it does not use JIT. Um, the JVM executes bytecode and makes Java portable across operating systems. Without JIT, the JVM interprets bytecode instruction by instruction, which is a lot slower. C and C++ compile directly to machine code natively, and it gives them faster startup and better performance. With JIT, Java can approach or match C and C++ performance in long running applications, and Java provides a balance of portability and runtime optimization, especially with JIT. And then I have sources here.